pi square plus pi power 4 divided by 8 pi power 6. Okay, while C0, C2 is going to be 0 and C3 is going to be 1. So C1 is positive, C3 is negative, so it's minus 315 times 1155 minus 125 pi square plus pi power 4 divided by 4 pi power 8. Okay, and C4 obviously going to be 0, and the C5 is going to be, what do you call, a vector that goes like 693 times 945 minus 153 pi square plus pi power 4 divided by 8 pi power 10 actually. So this is what that you're going to get. So take these constants and substitute them here. So this is going to be the orthogonal projection of sin x in, or this would be the best approximation of sin x. So in other words, the sin x is going to be approximately equal to this polynomial actually. So by substituting the values of C1, C2 and C3 and so on actually. So you will see now that when you plot this approximation, okay, of the sin x through, for example, computer, I would say try to find a difference. You will see that it's really hard to find the difference. They don't disagree at all at any point actually. So it would be, you know, a brilliant approximation of the function sin x actually. Okay? So this seems a hard calculation when you, for example, do it manually, but if you can write a routine, write a program, write a code actually, you know, and there are tools already available actually who can calculate, you know, a very good approximation of, you know, any kind of function, you know, on a given interval. Okay? And how you are calculating it? By expressing the orthogonal projection in the terms of the basis vectors and solving the normal equations. The solving normal equations give you coefficients and you get approximation. And that approximation works very well actually. Okay? That approximation works very well. Okay, so that's it on my side for today.